The basic definition is that of a Kakeya set. So you have a set K in FQ to the n, where FQ is a finite field of size Q. And you say this is a Kakeya set. This set is a Kakeya set. Or as Peter Sarnak likes to say, Kakeya. I'm not sure which is the correct. It's spelled with an E. If it contains a line in every direction. So formally, if for every direction V, it's a non-zero, there exists some point U such that the line through U in direction V is contained in K. So, and just to give context, so the question that we'd like to answer is, and this was asked by Wolff in '99. The question is, how small can it be? You have a line in every direction, can you be very small? And this was asked originally in the context of the famous Euclidean Kakeya conjecture. I'm not going to say much about it. I'm going to focus on finite fields, but again, it's a very famous conjecture saying that if you have a unit line segment in Rn, if you have a unit line segment in every direction, you must have high Minkowski or Hausdorff dimension. That's a famous open problem. It's still open in dimension 3 and above. And this was, Wolff's paper was talking about a lot of different aspects of this conjecture, and one of them was maybe to try to take the finite field version, where things are a bit nicer. You know, all lines have the same size intersection, and so on. There are no angles. You know, and this also came up independently in theoretical computer science. And I don't know if Avi was the first to notice the connection, but anyway, I learned about it from Avi when I was visiting here as a grad student. That if we can answer this question, there's actually a more general question in finite fields about distributions induced by this kind of structure, where you pick a random direction and you pick a random point on the line and so on. And these kind of questions come up in trying to construct extractors, which are similar to expander graphs. So we're trying to come up with explicit constructions of these random looking graphs. And this very simple constructions lead to these questions where you have to understand these things. So, so again, it came up independently, and so again, just to give by now we have a pretty much full, almost full understanding of this. So, following theorem. I'll state 3 papers because the constants got better. So I had the first one, then with Kopardi, Saraf, and Sudan. That was a bit later, and then so the better constant in the theorem, and then finally with not with just Book and Chow. Just a couple of years ago, they got the optimal constant. The theorem is that if K is a Kakeya set in FQ to the n, the size is at least, well, just write it this way, there's a constant depending on the dimension times Q to the n. So it has some fixed density. And the Cn, again, in these 3 papers were, initially it was n factorial, then it was 2 to the minus n, and then finally the tight constant turns out to be half. It took a long time for this half, but this is the best constant. So let me show you the construction. And the construction is the following. Take K, be the set. So x1 to xn such that for every I starting from 2, x2, let's say x1 squared plus plus xi is a quadratic residue 1 q. So there are n-1 equations. Each one cuts the size of the set by half. So this will have this density. And it's an exercise to show this is a Kakeya set. At least it contains line in every direction where the first coordinate is non-zero. So it has all the lines. There's a lot of lines, a lot of directions. Then you can add lines where the first coordinate is 0, and you would get a low order term. So this the main term is this, and then there's the low order terms that are there. Any questions by the way? Good. So this is the one-dimensional case, and before I go to the higher dimensional variant, I'd like to give you an idea of the proof techniques because it's interesting to see what fails for higher dimensions. So this proof will not work when we replace lines with planes, or at least not for the more complicated set. Okay, so just to give the high level idea of the proof, it uses the polynomial method. And the way the proof looks is you say, well, if the set is too small, let's say if k is much smaller, let's say just from the first bound, 1 over n factorial q to the n, then there exists a low degree polynomial and a non-zero polynomial f with degree not too large, let's say q minus 1, such that f vanishes on all the points in your set. So why? Because there are more monomials than this. You just count monomials, you can solve a system of equations and interpolate such a polynomial, and you have it. Each point in K gives you one condition, each monomial gives you 1 degree of freedom, and there are more monomials. Okay, and then you basically finish by saying that, well, for every direction V, there exists U such that F restricted to the line U plus TV is identically 0. So why is it identically 0? Because it's 0 on Q points, and its degree is at most Q minus 1. So it has to vanish identically on this line. And then this gives you a contradiction just by looking at several ways to see it. One way is to say, well, it has to vanish at the point at infinity, corresponding to V. And then it has to vanish basically identically at infinity, and it's impossible. So that's one way to do it. Another way is to look at the homogeneous part of highest degree, which doesn't involve any fancy words.
The polynomial homogeneous?
No. If it's homogeneous, you would lose one more here.
So then you speak of the dominant class?
Yeah, so the homogeneous part of highest degree of F must vanish at V for all V, and that's impossible. So this is the proof, and if you want to get the better constants, you have to work much harder. But this gives you some constant. And one thing to note that will be important later is this proof also works where you don't have all the points on the line. So even if I had q over 100 points on the line, I would still get a pretty good number. Or even q to some power, maybe q to the 0.9, I would still get a 0.9 here. It's a very robust proof. And it also works for curves and so on, but that's less important. We'll just focus on this. This particular point doesn't generalize to higher dimensions. Okay, so So let's move to a higher dimension and see what happens. So let's give the definition. Again, K. Let's call it D Kakeya. Right. If for every d-dimensional subspace V, this is the direction. So before the direction was a vector, now it's a d-dimensional subspace. Every d-dimensional subspace, you can shift it so that it's in your set. This U such that U plus D is in K. So this is a straightforward generalization. And right, so we'd like to say, ask about this kind of sets. And it turns out that using the polynomial method, you can actually get a very nice bound here that's qualitatively different than this. So you can get the same bound with a constant close to 1, basically. And this was observed very early, already in the paper of Ellenberg, Oberlin, and Tau. Then again, the constant was improved by Marty, Lev, Sudan. That K is D. Yeah, and D is at least 2, and you get something quite different. Then K is at least 1 minus epsilon to the n, where epsilon goes to 0, where the field size grows. I didn't mention it before, but typically in these problems, we think of the dimension as fixed and the field size growing. In applications and in computer science and so on, we do care about the dependency between Q and N. And actually, this theorem is for any Q. And it's interesting already when Q is, let's say, even a big constant. But typically, the nice way to think about it is just say N is fixed, it's 5 or 10, and Q is very large. So then you would get this kind of bound that basically tells you that there's no, the density cannot go, there are no interesting constructions like here.
One thing confused me.
Yeah.
If you take some FQ K, then a line in a vector space of FQK can be viewed as a k-dimensional subspace.
Right, but it wouldn't be in every direction. There would be directions defined by the big field.
Yes, sorry.
So yeah, you can get, if you want directions that if you view them in blocks, they come from a big field, then you can get them. Good point. All right, so if you really want all directions, there's nothing interesting. This really just uses the polynomial method with some extra tricks. And it's not surprising because if you try to run this strategy, you have a plane in every direction, you interpolate the polynomial. And this polynomial will have, let's say D is 2, you will have Q squared zeros on a plane, and then you can do something with that. If a polynomial vanishes at all points in a d-dimensional space, it gives you some information. However, if you're asking this more refined question of what happens when you have large intersection with a flat in every direction, then this proof doesn't work anymore. Because if you think of it, if you have a d-dimensional space, you'll have Q to the d points. you can have a linear function with q to the d minus 1 zeros. So once your number of points is less than that, this proof really doesn't work. And it turns out that, I mean, it's a really interesting question, what happens when you only have large intersections. It's something we kind of care about. So now we're going to look at this, we're going to give a definition that captures this more refined question. And this is the definition of a Furstenberg set. Okay. Now we have two parameters. One is this D, and the other one is M. This will be the number of points on the flat. So dm Furstenberg. For every d-dimensional subspace V, there exists a shift Q such that the size of the intersection of U plus V with your set is at least M. M is some number between Q to the D and 1. Okay, so again, the term Furstenberg set comes from the Euclidean question that asks about sets that have high dimension intersection with a line in every direction, or a flat or a disk in every direction. So it's inspired by those questions, and so the definition is clear. So we'd like to understand, given N, Q, D, and M, how small can this set? By the end of the talk, I'll give a pretty good answer for some most. So, and there's this.
Where does the name come from?
The what?
Why did you call it DM first?
Oh, I said that, so over the reals, their Furstenberg sets are sets that have a large Hausdorff dimension intersection with a line in every direction, or things. So and you like to deduce something about the Hausdorff dimension of the big set. So it's inspired by those questions. Right, so the first paper to get anything about this kind of question was theorem of Ellenberg and Ehrman. From 15, and it's a bit of a pattern here. There's a second paper that improves the constant, which is by Dar, Wolff, and Lund. So they actually generalize the question from sets to schemes. I'm not going to say much about it, but first let me say what the theorem is. So if K is EM Furstenberg, then the size of K is at least some constant, depending now on D and N, times M to the N over D. First, let's see, if M is Q to the D, then it's Kakeya, then this kind of works out. But when M is smaller, let's say Q to some power, Q to some alpha D, then this goes down pretty quickly. And again, this is this also holds for Furstenberg. schemes, and this is really not my specialty, but they for if you know what schemes are, they look instead of finite sets, they look at finite dimensional quotients of the polynomial ring. Quotient the polynomials by some ideal in a way that's finite dimensional. That's some type of scheme, some zero-dimensional scheme. And you can define this notion of Furstenberg set by taking this scheme modulo the equations of u plus v's, and say for every v there's u, such that this modulo those equations also has high dimension. Okay. So again, it's something that generalizes finite sets in a very big generalization, and this holds also for Furstenberg schemes. And for schemes, this is tight. So again, we rewrote their proof using more elementary techniques and improved the constant such that even the constant is at least asymptotically the right one. But the examples that show that this is tight are they're not sets. They're schemes where they have one point at the origin. They're very weird. They're not things you would get from a finite set. So you can get these from finite sets, but by taking all the polynomials vanishing on your set. This would be the way to get a schemed course.
The derivative of that point.
All the monomials up to some degree, yes, something like that. It's not very okay. So yeah, we worked really hard on understanding this proof and maybe improving it a little bit. And by the time we were done, we actually found a much nicer proof that works for sets and gets the right answer. And that was the first paper with Ben and Monique. And this is for Q sufficiently large. I think has to be at least. Remember right now, but yeah, it's for a large enough Q for sure.
And what did the examples that showed this is type look like?
Take monomials I to be the monomials of degree D. When D is large, D grows. And not this D, sorry, T. Take parameter T and take monomials of degree T. And it's the exponent is pretty much what you get. For any k-dimensional, any d-dimensional space, you get all monomials of degree T in D variables instead of n variables. So it's exactly this exponent. It's pretty cool that this is it's actually you can generalize it and prove something. And the proof is also incredibly beautiful. It's very different than the polynomial method. So it's something very elegant. But I'm not going to talk about it because at least for sets, it's not the right. Ended up not doing the right thing. Okay, so what we were able to show after that is that when there's at least two, M can't be too small. To the n q over epsilon squared. Then if k is dm Furstenberg, then it is at least minus epsilon m to the n minus d. And for now, let's think of n as fixed, just so we know what's going on. N is fixed, so this is a constant times q. So the intersection is not too small. At least some constant times q. And then you basically get something that's much stronger, at least from this, right? It's pretty close to q to the n. Maybe you lose a little bit.
Oh, it's epsilon.
Oh, epsilon comes here. So if m is big enough, you get closer and closer to the. This also has an implicit bound on q. this implies that Q is at least some exponential to the n or n over d, because m is at most q to the d. So if q was too small, this wouldn't hold. So it's for large fields. It's for very large fields. So now comes the funny part. So I claim this is tight. And I wonder if anybody can think of an example in upper bound. So by tight, I mean that if you drop the 1 minus epsilon, there are sets of this size.
Just take a codimension one subspace.
That works. Not codimension one. Well, you need m points in every direction.
Well, it depends. For d equals 2, you need.
Well, you don't know what I mean. M is some number between the q and q squared, right?
Yeah.
So how do you get that?
So you take some cosine.
Okay. I mean, yeah. If you take enough cosets, you get the right. If you get this size, but well, I claim there's something easier. With any set of size m q to the n minus d is the m Furstenberg. By the pigeonhole argument, for every direction, take a subspace in the direction and look at all of its shifts. It partitions the space into this many disjoint sets. So one of them must have m points. That's the punchline, the joke. Good. Yeah, I couldn't find a joke about schemes, but this is close enough. Okay, so now we actually have an even stronger version of this theorem in the second paper with Manik, but before that I want to give the high level idea of the proof of this, and then from that I think you'll be maybe more clear how can you generalize this, and why can you prove something stronger. What's the proof idea? It's nice to look at a certain graph. I'm just going to look at d equals 2. Right. So we're looking at two-dimensional flats in every direction. When I say flat, I mean a shift of a subspace. So we have two-dimensional flats in every direction. And we're interested in how many points are on them, on the union. But we can look in the intermediate thing of all the lines contained in them. Actually, no, we have flats that have many points, and we're interested in how many points on them. So we're going to look at this graph that has points at this side, the q to the n point. For each, when I draw this line, I mean it's like the vertices of a graph. Then you have another layer of lines. And the lines are grouped into parallel lines. So let's say all the vertices here correspond to shifts of the same line, and all the vertices here are shifts of another line, and so on. So we have all the lines, and then we connect the line to all of its q points. Okay. And then we do another layer of two flats, again grouped by direction. So these will be shifts of one flat, and we connect each one to the q, sorry, not q squared lines, but almost q squared lines. So we connect it to about q squared lines in this flat. So from the flat we go to lines, from the lines we go to points. So the graph is well defined. What is the one dimension? So I already erased it, but the one-dimensional Kakeya problem, for which we have the polynomial method and all these nice bounds. The one-dimensional bound tells us that if you have take a vertex from each block, a line in every direction, then if you look at their neighbors, it's like this is why it comes up with expanders. It's an expansion statement. You have a set of neighbors is at least Cn q to the n. So this really, it's a set that has more neighbors than the size of the set. This is really an expander for some, not for every subset, for some subsets. Okay, so this point is clear why this is. So we know this. We know if you have one in each block, there are q to the n minus 1 blocks, and instead you have Cn q to the n neighbors.
So each layer, they are just vertices, right? There is no connection between
each layer. What do you mean?
Like each vertical line you drew.
Yeah. There are no edges connecting vertices on each. So these are two bipartite graphs. Questions? Okay. So it turns out that you can take this theorem and you can shift it one layer up. It's not very hard. So what happens when you shift it one layer up? You get that if you have two flat, one in each direction, and you look at all the lines contained in them, then you would get Cn fraction. It's even more than that. You get Cn fraction in each block. That's not very hard to show. Just the same proof here. You just kind of move it up. You apply it in each block somehow. You reduce the dimension by 1 in each block. So if you have a two flat in every direction, they would. If you look at all the lines contained in all these two flats, you would get a good fraction of all the lines. And so now we'd like to use that to say something about sets with too many heavy, with a heavy two flat in every direction. So what happens if I have, these are all, let's call them M-rich. This is the technical term for a flat that has a lot of points in your set. That's a rich flat. So these are I have an M-rich flat in every block. So how can I use this theorem about lines? Well, if my, let's say if I have an M-rich flat, it's a two-dimensional flat, so at least M points from my original set in it. What happens, so I'm going to look at all the lines in this flat. So I claim that just by pairwise independence, by kind of a sample, if I pick a random line, I get a pairwise independent sample. So if this M is big enough, most lines will have the right number of points on them. Now, most lines are going to be M over K, maybe with some small loss, maybe 1 plus epsilon, 1 minus epsilon. But they'll be on average, at least they'll be M over Q rich. Right? And if the parameters, if Q is big enough, they'll be concentrated around the expectation because of pairwise independence, because of variance. So what I get is that most of these are M over Q rich, right, for each one. So then the next step is to say, well, when I take a random one, I pick one of these at random and I take a random line in it, it's not that I hit a lot of lines. I actually hit a lot of lines here with a nice distribution. It can't be too concentrated. And this is something you can use polynomial method to show. And then you get that most lines, not most lines, but many lines here are m over q, maybe 1 minus epsilon m over q rich. So we went from having a rich flat in every direction to having many rich lines. And they have many rich lines, that's already straightforward. So they're just, again, the same type of argument with variance and expectation finish the job.
Sorry, are you giving a new proof of your theorem without using?
No, I'm using that theorem. I'm using that
it as the
theorem
last step.
to show that if you take a two flat in every direction, they would contain many lines. I'm shifting my theorem from here to here.
No, right. But let's take your from lines to points.
Yes.
It's not a new proof. You're going to use a polynomial method there or not?
No, so now I don't have a line in every direction. After this whole thing, I get
distribution.
It's almost all lines. It's a constant fraction of all the lines.
So let's go back to just the first step.
Yeah.
Is this a new proof of your theorem?
No, the polynomial method is used. So we know the polynomial method here.
Use it there.
I'm shifting it here. It's the same polynomial method. I say that if I have a flat in every direction, they contain many lines.
Okay.
Then I say, well, many of these lines will be too heavy. So many of these lines will be too heavy. Now I already have a huge number of lines. That's the idea. There's some technicalities, but overall, that's the main idea.
So this huge set of lines, you don't take into account whether many are parallels or not.
Over here, I actually get the constant fraction of the lines in every block. That's, we don't use it. Okay, no questions? Good, so that's the idea, and then it gives us somehow an indication of what we can show that's a little beyond that. So the same proof would work if I replace rich with poor, right? Because how did this? What was the final contradiction? We said I assumed that my set was too small, and I ended up with too many rich lines. And it contradicts just basic sampling of lines. But what if this was these were poor flats, or flats with too few points? Or in other words, let's say I have at most m points on every flat, on a flat in every direction. Can I show that my set has to be small, right? And the same proof would work. I would do the same theorem here, that going from one in each direction to many lines, I would get that by sampling each poor one will have many poor lines. I'll get too many poor lines, contradicting the variance. It's two-sided. Okay, so why not just do everything together? Why not just define the unbalanced flat and unbalanced line and show something like for okay, so let's write it down, at least what we would like to say. Let's give a definition of this unbalancedness. Have a D flat. Now it means, again, it will be affine. It doesn't have to be through the origin. D flat B is epsilon balanced with respect to K. If it has about the right size of an intersection. So intersection is what it's supposed to be, what the expectation would be for a random subspace. It's within this range up to an epsilon. And we would like to say, something along the following lines, is that you cannot have unbalanced flat in every direction. It's kind of what this proof would give. If you have if you have an unbalanced one in every direction, then many of the lines in an unbalanced one, if it's big or small, it doesn't matter. Many of the lines will be unbalanced. Then you get too many unbalanced lines. So that would be a contradiction. So we basically get this, and again, there's a bunch of parameters to state, but I'll write it up there. There with Manigdar. Ben unfortunately left us for Korea, so it's not okay. And has to be at least 5. Q has to be at least 32n over epsilon squared delta squared. That delta is going to come in, and there'll be something extra with delta, but you can ignore it for now. And let R, another parameter, R is between 4 and n-1 be such that the size of your set is between q to the r plus 1 and q to the r. This r is important because this will tell us what dimensionals, what d do we need to take, because it's not this two-dimensional thing will only work with very large sets of constant density. But if you want to do it for any set, we have to pick the dimension to be the dimension we can take is n minus r plus 3. So n minus r is obvious, right? If it's less than n minus r, you're not going to see your set at all. We need plus 3 because, well, we're not going to do this two-step. We're actually going to take another level. For technical reasons, this Cn here is not good enough for us. We want it to be 1. So we're going to use the two-dimensional Kakeya for full sets to get. So if you do 2 steps, you get 1. You get almost everything. So we need that. So we need to take 3 steps. So this is why this 3 is there. This is also why the Q is not exponential. It's linear. And I think you could replace 3 by 2 if you can. If you want to take much larger Q. And then yeah, 1 minus delta fraction of all d-dimensional subspecies V are such that U plus V is epsilon balanced for all U. Okay, so we wanted to say that there is no, that there are no, you cannot have an unbalanced flat in every direction. Equivalently, logically, the same thing is saying there has to exist some direction such that all of its shifts are balanced. Okay. So this is even stronger. It tells you that most directions, all of the shifts are balanced. So, and this delta comes here also. So it's that's the kind of the strongest theorem we could prove, and the proof is along these lines, maybe with a few more details. Right, so another nice way to think about it is you have some arbitrary set, and you can find even without this 1 minus delta, even just the existence. So you can find a direction such that if you slice it with a d-dimensional flat in this direction, all of the slices will have the same number of points up to 1 plus minus epsilon. This is a property that if K was a subspace, right? This was obvious. But somehow you can get the same, if K was a subspace, you can do this where all the intersections are 1. But for any set, you can do it where the intersections are not very large. Let's say, we have to kind of think about it. So this extra 3 here tells you that the intersections will be something like Q cubed. For example, you can try, I mean, we're thinking a little bit about, we can apply this for varieties over FQ to the N, and we get it in some direction, all the slices are somehow have about the same number of points. And it gives you some information about, we know that the number of points is determined by, more algebraic things like degree and anyway, it'll be nice to find more applications of it. I'll talk about a couple of applications, but I think this might have more, just applying it on interesting sets and seeing if it gives anything might be interesting. Maybe before any questions?
Allow you to reduce the dimension of a problem about high dimensional variety.
Maybe.
Because it goes down.
Somehow you always know that if you take any set and you take a random subspace, you get the right number. You get about the right number of things. This does it. You can slice it into disjoint. Other questions? Okay, maybe I'll mention a couple of applications. So one application, I don't know if it's really an application, it's almost an immediate corollary, but it relates to a well-known theorem in theoretical computer science called the leftover hash lemma. Very famous result of also again in 89, one of the most used lemmas in theoretical computer science, in cryptography, and in a lot of places. So this lemma tells you that if you have a random variable x distributed on the Boolean cube, so let me write f2 to the n. And the mean entropy x is at least k. Mean entropy is just an L infinity version of entropy. So it just means that the probability that x is equal to some particular value is at most 2 to the minus k. It's a L infinity bounded random variable. You can think of it could be uniform on a set of size 2 to the k. Then if you pick a linear function, you're trying to extract the randomness. So you're trying to map it in a uniform way to some smaller set. So it's like a hash function. So you take, if you pick a function, a linear function at random, from f2 to the n, to f2 to the k minus t. So this t, in this particular lemma, you need t to be 1 over epsilon. This is called the entropy loss. And again, with high probability, L of x is epsilon close the uniform distribution in L1 distance. L1 distance in this case is basically the statistical distance between distributions up to a factor of 2. So what does it say? It says that if you take a distribution with k bits of entropy and you hash it down to k minus log 2 log 1 over epsilon bits, so you get something that's close to uniform and without knowing anything about x. It can be any distribution. So this is very useful. For example, if, let's say you have a random key shared, random string shared between two parties, and some information about that string is leaked, but you don't know which information. So an adversary learns something about your string, but not all of it. Then you can pick a random linear function. You can send it in the plane. You can each apply it to your random string and get something that's as good as random for as much entropy as you could basically hope to get.
So L is something random? Or?
Yeah, you pick it, yes, thank you. It's random. Thank you. Yeah, uniformly it's random. Random linear function. It really comes up in a lot of places. So it's a great tool. And it's not very hard for
How did they prove?
How did they prove it? Putting me on the spot. I don't remember. I remember seeing it a long time ago. I'll remember.
You try to map 2 points from it. You look at the probability of
Yes, collision probability. Yeah, it's just looking at the collision probability. It's like the L2 entropy. And L2 and L1 become.
And then you get from it an L1.
Yeah. When the L2 norm of the distribution goes down sufficiently, the L1 becomes close to uniform.
Is F2 important here?
No, it's not. And for larger fields, I mean, no, it's just because it comes from cryptography and so on. It's natural to look at bits here. And so what we can prove is more pretty direct corollary of that theorem. Why is this even relevant? I mean, if you think about this statement where you have a set K, think of X as uniform on the set K. If I find a direction that slices it equally, it means that if I project it in this direction, right? Think of this subspace as a kernel of a linear map. If I project it in this direction, the slices are the shifts of the kernel are exactly the points, and the intersection is exactly the probability of each point. So what do I hope to get? I can hope to get like an L infinity version of that lemma, where I pick a random linear map, I get every point with almost the same probability. And you can do it, and it's nice to state it over F2 because that's where this is coming from, but yeah, here we need K to be big. So what do? We just break, we take Q to be a power of 2 and take a big field. And then at the end, you have to do something extra because exactly what came up before is that the random linear function over a big field is not the random linear function over the small field. But you can prove, again, the corollary of that theorem is that, yeah, and under the same setting, if you take the entropy loss to be slightly bigger, so the entropy loss is O of log n over epsilon. Then, and under the same setting, L of x is, so epsilon over 2 to the k minus t close uniform in L infinity norm. So 1 over, the uniform distribution has 1 over 2 to the k minus t at every point. This distribution will be, at every point you would get this. So the error, the L infinity error is this. And I should say, okay, so corollary from that theorem is that this is true for x when x is uniform over a set. It's a flat distribution. It takes more work. That's actually another paper that Monique is writing. It takes more work to generalize it to our arbitrary distributions because they're.
But does your picture continue to apply, replacing k by a probability distribution?
Yeah, now they're weights. So you have to work harder. So again, Monique told me that it works and he's writing it down, so I can quote it as his result. But yeah, it takes some more work to go from a set to a distribution, which interestingly, in L1 you don't have to, because in L1 any distribution of mean entropy k is a convex combination of flat distributions. And then this result, it's enough to prove it for sets. But over here, because of this infinity thing, it doesn't work. You can't just use the kind of trick. Okay, there's another application that from was mentioned the authors, and I'm not going to say much about it. About just it's not published yet. It's a theorem of Ordentlich. Oded Regev and Barak Weiss. And so actually this work kind of started by them asking us a question. They had a paper a few years ago on lattice coverings that they improved the result of Rogers from the 50s about you have a convex set in Rn, and you're asking about how much you're allowed to dilate it so that maybe it's a little bigger, but once you dilate it enough, it has enough volume, you'd like to say that there exists a co-volume 1 lattice such that if you shift it by this lattice, it covers all of space. So the covering number of this convex, but the covering number, maybe it's not the technical term, but it's a certain, you would like to know what's the volume of, what volume do you need to dilate it to so that there will be a co-volume 1 lattice that covers it with it. And they showed a few years ago that it's something like n dimension is n. This number is n squared instead of n to the log n, which was known before. They used the Kakeya results, two-dimensional Kakeya results in finite fields, oddly, for full sets when you have a flat in every direction. They use this 1 minus epsilon results of it was stated there before. And somehow the way you pick this lattice is by dividing every cell into p parts and picking some random subspace. So it comes up, these finite field problems come up even in this type of questions. And this result allows them to strengthen their result to get uniform covering, so that every point is covered by the same number of translates under about the same.
The finite field will be unfree.
Yeah.
The finite field they use will be FP with P.
Yes. Because you start with some lattice that has relatively good parameters, and then you refine it by dividing the cell into every segment into p parts, and doing some random thing there. So it's another interesting. Okay, so I think I'm out of time.
Questions?
This high-dimension Kakeya problem over the reals, is it?
Good question.
Yeah.
So it's so again the question is if you have a set, a compact set in Rn, and you have let's say a unit measure disk, two-dimensional disk in every orientation. So it's not known even if this can have measure 0. It might be that those sets. So I think the best thing that's known is that if you have a log n dimensional disk in every direction, then the Bourgain showed that that's positive measure. And between 2 and log n, it's open. So this results suggest, I think, that if something like this could be done over the reals, this might suggest that two-dimensional disks already give you positive measure, but we don't yet know how to show it. over the p-adics, again, this is another result Monique is writing that I haven't seen, is that the recent resolution of the Kakeya conjecture by Arsovsky over the p-adics, combined with this, can show that the two-dimensional Kakeya sets over the p-adics have positive measure.
Second question.
It is wrong.
Does this polynomial method, does it bring a path towards the real Kakeya sets in province of the
It's a
kind?
good question. So I'm not the person to ask, and there are people that know more about it, but there are results. So the Kakeya conjecture over the reals is at the end of a chain of stronger conjectures. And I think for the stronger conjectures, the polynomial method has been used to get new results. Because what was known before was even less. So for the Euclidean Kakeya conjecture, there's a very powerful technique of again Bourgain and Katz and Tao using additive combinatorics that gives you some bounds. But for the stronger conjectures, this wasn't there. So you could get something with polynomial techniques.
Okay, let's thank Zeev again.